Hello, good morning or good afternoon, depending on your time zone. My name is Robert Schoenberger. I'm the editor-in-chief of IndustryWeek. And welcome to Production Pulse, our bi-weekly look at news in the manufacturing world, where we'll interview top people from major companies to discuss important things going on across that landscape. Today I have Charles Poon from Ford Motor Company, who is their Director of Electrical Vehicle Systems Engineering. Do I have that right, Charles?
Yeah, electrified systems, primarily in propulsion.
Great. And Charles is going to talk to us about Ford's recent investment of $3.5 billion in Michigan to build a plant making lithium iron phosphate batteries. That was just came out last month and made a big splash. And this is a new battery chemistry. Well, it's new to Ford, new to certain automotive productions. Can you just talk a little bit about what lithium iron phosphate is, how it differs from the traditional lithium ion batteries people hear about for electric vehicles, and what are some of the advantages here?
Yeah. So first of all, Robert, thanks for inviting me. Appreciate the opportunity to talk about some of our plans and especially our introduction of lithium iron phosphate batteries. So as you just highlighted, lithium iron phosphate batteries are different than, let's say, most of the batteries that you probably see in electric vehicles today. And most electric vehicles use a chemistry called NCM, or nickel, cobalt, manganese. And that particular chemistry has some advantages in which it has very high energy density. And therefore, you're able to put quite a bit of energy within a certain given volume. And that's what's called volumetric energy efficiency. But it also has some disadvantages, especially with the scarcity of some of the raw materials and the cost of those raw materials, especially for nickel and cobalt. And the lithium iron phosphate is a new chemistry that we're introducing within the Ford portfolio, and it stands for lithium iron phosphate. And what that is the active material that's in the cathode of a battery cell. And some unique properties that we're trying to take advantage of for lithium iron phosphate, its durability, its ability to be able to take frequent charges up to 100% and potentially be able to charge faster than an NCM. And lastly, it's also capable, to potentially be more durable as well over the long term. So it's something that we're really trying to take advantage of as part of our battery design.
Great. And yeah, there are some pictures I've seen of them. The lithium manganese cobalt batteries, they're more that pouch style, where the lithium iron phosphate, I think we're seeing a picture on the screen right here, look a little more like closer to a traditional, what we consider like the little lead acid car batteries, so that plastic housing on that. Can you talk a little bit about why the form factor is so different on those two?
Yeah. So one of the reasons that we like to focus on pouch-based type of form factors for nickel, cobalt, manganese is because we want to try to increase the amount of energy density for those specific applications. And so pouch-based dense formats tend to offer advantages in how you package it and how you're able to design a battery pack around it. With lithium iron phosphate, because it has a slightly lower energy density, we have to figure out ways to be able to design the cell in such a way that at the battery pack level, that we can offset the lower energy density in the cell for higher energy density in the pack. And we do that by using a strategy called cell to pack type of format, where we take advantage of the built-in structure that's in the prismatic that you see in the video right here on the right. And we're putting the LFP chemistry into that structure that itself is able to handle certain loads. And then when we design it inside a battery pack, we're able to offset the lower energy density of the LFP and chemistry and still be able to essentially deliver the same standard range that our current standard range NCM is able to provide today.
So outside of, you talked about some of the material costs, or the materials are a little easier to source. There's some cost differences between the lithium ion and the LFP batteries. Are there any other manufacturing advantages? Are they any easier to make? Because we are a manufacturing publication over here. Are they any easier to make going to those kind of those square style batteries instead of the pouches?
Yeah, because of the unique chemistry properties, we can actually put more energy per unit cell block. So, for instance, you'll notice that the pouch cell there on the left in that prior picture was a bit smaller than the very large volume that's occupied by the prismatic form factor of an LFP cell. And because of that, we can take advantage of being able to put more active material per unit volume. So the amount of capital that is required to manufacture a cell, whether it's the mixers or the coaters, the slitters and the dryers, all the way up to packaging, can be utilized more effectively because we're able to put more energy per unit volume.
Great. We've talked about as an industry this push for electrification. There are massive investments going on between Ford and Honda, Toyota, General Motors. Everyone is really diving all in on electrified vehicles, but the cost remains very high for the consumer. How much of an impact are new battery chemistries going to have in getting those costs down to where these vehicles might be more attractive to the average, sedan buyer or average small SUV buyer?
Yeah, it has very large implications. I think unlike a traditional ICE-based propulsion system, a EV propulsion system, the total cost can be as much as 40 to 50% of the total cost of the vehicle. Of that, most of that cost is actually in the battery, and the majority of the cost of that makes up the battery is really the active material within the battery cell. So anywhere you can go and identify lower cost alternatives that have equivalent performance, or maybe different performance that you can then target certain specific users that iron phosphate would be good for. For instance, like customers that do more predictable and frequent trips that need more charging to 100%, then we can offer these other chemistries for those customers that are operating their vehicles in a slightly different way versus someone that needs more power, a lot more range. Then NCM may benefit from them. But ultimately, chemistry is going to play a huge part in being able to deliver affordable choices for our customers based off of their vehicle usage.
You talk to car buyers today, the traditional internal combustion engine buyers today. There's a lot of sophistication in that audience that everyone knows what a V8 is versus a V6 versus an i4. You can tell anyone that I'm getting the turbocharged four-cylinder. It's as powerful as a V6. That took, a century of development to get customers to the point where everyone knows what these things mean. How big is the learning curve going to be for the average car buyer to understand the difference between an LFP battery and an NCM battery or other battery chemistries? Is it going to be the same sort of thing, the difference between a V6 and an i4 or a V8, or is it going to be a whole different kind of understanding that people are going to have to develop?
Yeah, I think it's going to be a little bit of both. What we want to try to do at Ford is being able to select the right chemistries for the right customers in the right segments. So, for instance, this lithium iron phosphate that we're offering it as a standard range, primarily because it suits the usage profiles of those customers that we know of and that we are very close to. And so we want to try to take some of that ambiguity and some of that confusion from the customers and from consumers to be able to have to choose for themselves, because we know what some of those advantages are, and we're able to then design a battery pack and a vehicle that takes advantage of those for specific customer use cases. The chemistry and the chemistry performance within a battery pack and within an electric vehicle can be quite complicated, and we want to be able to use some of our know-how to be able to offer specific chemistries for specific work and energy use conditions that are required. So yeah, I believe it's going to take some time, but I think over time you're going to likely see more and more offerings and more segmentation of chemistries to be able to make sure that we can provide the most optimal solution for specific use cases.
Yeah, it sounds pretty obvious that, say you have the daily commuter, the person is going back within maybe a 30-mile range, that lithium iron phosphate might be the perfect battery for them because they're maybe charging a little more frequently, but they're not using the full capacity to go long distances. Whereas maybe someone using that F-150 who's not only, hauling material, but maybe going significantly further distances to job sites, things like that, maybe they're a better candidate for this other. Do you expect to have different chemistries available within the same vehicle, or does that create such an engineering challenge because you have to design two completely different battery styles for the end vehicle?
Yeah, it's a great question. We planned our vehicle architectures and our battery designs to be flexible to allow us to take advantage of cell chemistries that offer benefits for our customers. So in this particular case, we are planning to offer both a NCM extended range battery offering on the Mach-E, for instance, as well as we're going to introduce the standard range battery in the LFP format. And in this particular case, we were able to accommodate not only cell chemistries, but the different formats that you previously shown to be able to optimize the battery design, the cost, the durability, the reliability, and the software controls associated with it, all within one platform. So we are trying to make sure that we have that flexibility to be able to introduce chemistries when they are made available.
Yeah, this is 2023, and everything is political these days. And there has been some noise about Ford licensing technology on the lithium iron phosphate batteries from CATL, which is a Chinese-owned company. Is that a concern that there is Chinese technology, or is this just a matter of you've licensed a product from a technology company, as automakers have done for over 100 years now?
Yeah, it's very similar to what you just described. I would say that our business arrangement is a fully owned facility in Marshall that's going to be producing our new iron phosphate batteries. And we are leveraging the largest battery supplier in the world who specializes in iron phosphate. And we are licensing that technology in which Ford is then going to build those cells and we are going to be ourselves integrating them into battery packs over time. And so it's very similar to, I think, for us to access that technology as quickly as possible so that we can find lower cost solutions for those customers, that have a different usage pattern that don't necessarily need NCM, in which that raw material is quite expensive today. I think also second, it gives us the opportunity to be able to scale much faster than if we were just relying on a limited supply of raw materials for nickel and cobalt especially. And so it offers a lot of advantages for us that we will be able to pass on to our customers.
That's great. Well, Charles, thank you so much. And actually, thank you for joining us from London today. This is an international version, I guess, of our Production Pulse biweekly live stream here. Thank you for your information. This is great. I mean, it's such an exciting time in the automotive industry right now to see these investments and just seeing every major automaker really rethinking how it's going to approach this century-old industry and bring it into the 21st, 22nd century. So thanks for your time today. I really appreciate it.
Yeah, thanks for having me.